that this Norman window is a rectangular base. So down here is a rectangular base. And it has a semicircle at the top, half of a circle. And the whole perimeter, what I mean by the whole perimeter is if I started at this corner right here and went along here, here, around here, and back down to here, then that whole thing, all of those distances added together would be 16. That's what it says. Outside frame of the window is 16 meters. So all of those things added together would be 16. The other thing you need to appreciate is that the width of the window at the base right here, where I'm pointing to, down here, that width would correspond to the diameter of this circle, right? That makes sense because the semicircle sits right on top of that rectangle. So if I were to make, and here's what I'm going to choose to do. I'm going to put the center of the circle right here. And let me erase these other lines that I don't really need right now. Let's get rid of those. If I were to make this line at the top here, let's call it X, right, as the radius of the circle, then obviously, hopefully obvious, then this line down here would be 2x, right? Because that represents the radius doubled, which is really the diameter of this thing, by the way, the diameter of that semicircle. And this thing over here, we could call the length, if you like, or the height. Let's say height of the rectangle. And what we would therefore say is that when we add together all of these different dimensions, that we would get that 16 meters that's on top there. Well, what about the length of this line? How much is the length of this line right here? Right? Well, how would I do that? How would I find the length of that? Because that's part of the perimeter, right? What is the length of that perimeter? Right? That part of the semicircle right there. Come on, jump in with that, with a response to that, please. What is the length of that line that I just wrote on there? Right? Remember that it's part of a circle that has a radius of x, right? And we know it's half of, exactly, it's half the circumference. And to get the circumference, it's 2 pi r, as you know. So we're going to divide that by 2 because it's a semicircle. So it's really just pi times x. I said r, but in this case, it's actually x, pi times x, right? So it's a 2 pi r, which is what a whole a whole circle would be. But then you're dividing that by 2 because it's a half of it. So that represents what that is. So the total length of this thing, which we said is 16, by the way, right, would be the 2x here plus the h. Well, let's just say 2h because obviously there are 2 h's. So 2x plus 2h, right, plus the pi times the x is what is equal to 16. All right, let me go with that again. 2x plus h plus another h, so 2h, and then this half of the circle is pi times x is equal to 16. And then what you might want to do is say, well, why don't we isolate the h in this case? So 2h is equal to 16 minus the 2x minus the pi x. Okay, so then h, of course, is equal to all of this divided by 2. And this could actually simplify, just so you know. And it almost looks as if I'm doing the whole thing, but I'm not. I'm doing part of it just to give an idea of what to do. So this is going to equal to 8. I'm dividing each of these by 2 minus x minus a half pi x. That's what my h is. Now, the volume, not the volume, the area, that's not volume, it's just area. We're trying to, it says maximize the area of the window. That's what Jack wants to do. He wants to get as much sunlight through this window as possible. So he wants to maximize the area. So let's get a formula for area. The formula for area, if you think about it, would be area is equal to the length and the width multiplied as h times 2x, right, plus If you go back to the diagram, the formula for the area of a circle is, of course, pi r squared. We're going to say x in this case, pi x squared divided by 2, right? So that means that I'm going to take the pi x squared divided by 2, and those two together would represent my total area. What do you think I'm going to do next, folks? Because I don't want to have two variables here. We've done this a million times before. Well, not quite. What Taj says, sub in the h, absolutely. We have an equation for h. And as you can see, it's going to get into a really messy algebraic question, but I'll just put that in and then I'll leave it there. So this is equal to this thing here, which is 8 minus x. By the way, you can factor out a common factor of x out of this, but I'll leave it as it is for now. Minus a half pi x multiplied by 2x, and then plus pi x squared over 2, right? So this is a function now that's exclusively in terms of x. And yes, this is what you're going to have to derive at this point. But let me give you the bottom line. Let me just cut to the chase here, right? It always works out to be the following, right? When you set this equal to 0, well, first of all, when you derive this, right, which you're not going to do, right, and you set it equal to 0 and you solve it, and then you get the x value that gives you a maximum. The x that works out to be the maximum, the x that maximizes the x value that maximizes the area, sorry, that maxes the area, always works out to be the perimeter that we wanted divided by pi plus 4. Always, always. Okay? So in this case, because the perimeter that we want is 16, is going to be equal to 16 over pi plus 4. So it doesn't matter what number you put in as that perimeter. It just works out to be that number over pi plus 4. So I'm thinking, do I want to go through all of the acrobatics of the algebra that's involved in this and the derivative that's involved in this and all of that good stuff? And what do I mean always? That's exactly what I mean, Stephen. I'm saying that if you have a Norman window, right? And in this case, this Norman window has a perimeter of 16, that the radius of that window that maximizes the area. Oh, just for Norman windows. Yeah. Just for Norman windows. That's what I'm talking about. For this kind of shape. If you want to maximize the area, you make the radius equal to the perimeter over x plus 4. That's what I'm talking about. All right. All right. And turns out the height is also the same thing, by the way. But I'm going to leave that. And if you look at the answer, you'll see that that's exactly what the answer is. And if you are bored and you really feel as if you want to challenge yourself with some algebra, you go ahead and sink your teeth into that. Be my guest. But I'm not putting it on the problem set. So that may not be much of an incentive for you to do that. But some of you are really into crunching numbers, so go right ahead. I've shown you how to get started, and you are welcome to finish up if you really want something to challenge you. All right? Okay, I'm going to move along. I've shown you how it can be done, but I'm going to move along. And I also showed you how you can just get to the answer without doing much of all this stuff here. All right, let's get to this one. And I think it might have been, was it Carly? Carly, was you that was doing this question on your own and we're working on? Was it Carly? Carly, was it you, right? I'm thinking it was. Yes, it was. Okay. Maybe I should just turn it over to you and ask you to do it. But anyway, let's keep going. Did you eventually get the answers that were given? Did you eventually? You didn't. Oh, okay. All right. Well, let's see what we can do with this then. So open container must hold 2 liters of liquid. 1 liter is 1,000 centimeters cubed. It's a volume, right? The material for the bottom costs, and they give you an equation for that. And material for the body costs, and they give you, not an equation, they give you a number for that. What are the dimensions of the least expensive container rounded to 2 decimal places? Okay. So do I try to draw this thing? What the heck? Sure, why not? Right? Let them all laugh at your terrible drawings. So inside of this thing, we need 2 liters. And the formula for volume, as you know, is pi r squared height. That's the formula for volume. And the formula for surface area is 2 pi r squared plus 2 pi r h. Just for the record, the 2 circles, so this circle at the top, the circle at the bottom, those 2 circles are why we have the 2 pi r squared here, because we have 2 circles that are part of the surface area. Okay? And what I was about to say to you is that this part of the function here, right, of the formula here, is the body of the cylinder. That's the part that's going to be 8 cents per centimeter squared. This part of the formula here that I'm pointing to, that represents the cost of the bottom. Oh, it's an open cylinder. Oh, you know what I just realized? And I think this might be the issue with you as well, Carly. If it's an open cylinder, it's not going to be 2 pi r squared, right? Because can everybody see what I'm saying here? If it's open and it's the bottom that we're going to be dealing with, it means that it's not going to be 2, it's just going to be pi r squared. So I'm going to actually erase, here me erasing again. I'm actually going to erase that 2 right there. So, Carly, if you didn't get it, it's probably because of that. Right? In this case, it's just pi r squared. Why? Because it says an open container, which means that it only has one circle. So the circle at the bottom, this one down here, is going to represent that pi r squared. And then the body, which is the outside of the can, like the lateral surface area, that's your 2 pi r h. Does that make sense, everybody? First of all, before I go any further, that the open part of it means that I'm only looking at one of the circles. Okay, Taj is good with that. Everybody else makes sense? Okay, so Carly, I think that might have been the issue with your question. In fact, I think when you showed it to me, I didn't even pay attention to that. Okay, so let us now set the volume equal to this 2000 liters centimeter cubed, right? Because it told us that. It told us that this pi r squared h is equal to 2000. All right. So I'm thinking, all right, that means that my h is equal to 2000 divided by pi r squared. All right. Now I'm ready to put this all into my surface area formula. And my surface area now, this is without the costs. This is before we get to the cost. We'll get to the costs in a minute. My surface area is just going to be equal to pi r squared plus 2 pi r 2000 over pi r squared. Okay, which if I simplify the second part of this, pi r squared, that's 2 times 2000, which is 4000. And that pi will cancel out. I'm going to be left with 1r at the bottom here still. Okay, now that's just a generic equation that does not yet involve costs, right? That's just the surface area generally. Now, to get surface area with cost in it, we're going to have to multiply each part of this by the cost associated with it. So that 0.06 gets multiplied by the bottom, which is the pi r squared, and the 0.08 gets multiplied by the lateral surface area around the sides of this cylindrical open can. Okay, so I'm going to take the pi r squared and multiply that by 0.06 pi r squared. Right? This is SA with costs now. SA with the cost involved. The cost of the material, that is. So 0.06 times pi r squared plus 0.08 times 4000 over r. Let me just make sure I got them in the right order. I think it was 6 cents and 8 cents. 6 cents was for the bottom, right? So that's the pi r squared part. And the body was 8 cents. Okay, so I think we're good there. All right. So this second part here, we can actually make a little bit easier by taking 0.8 times the 400. So let's just keep it So it's simplest form possible. This is again costs. So 0.06, I don't know why I need to. All right, let's just undo it rather than trying to erase it. So 0.06 pi r squared. And I can multiply that 0.8 times that 0.08, excuse me, times that 4,000. And I believe that's going to be 32. Double check that for me, please, over R. 0.08 times 4,000. Is that 32? Help me out there, please, folks. Is that 32? Did I get that right? I don't think it's 320. 8 times 4 is 32. Yeah. Oh, 320. It is 320. Okay, then. Did you take 0.08 or 0.8? You sure you got it? I mean, I want to be sure I'm right. It is 320. Oh, okay. All right. All right. Okay. 320. All right. No problem. Okay. Excuse me. Actually, that makes sense. Okay, that's close to 10%, which should be about 400. Okay. All right. Thank you. All right. So now we're going to get our derivative. All right. And our derivative, so it's the s prime of x would be equal to, again, you want to double check me on this, 0.12 pi r minus, I'm going to say 320 over r squared is what I'm getting from that, right? Of course, that r is like r to the minus 1, and r to the minus 1 times 320 would be minus 320 r to the minus 2, which is the same thing as what I just got there. Okay? And this is what we're going to set equal to 0. So it really means that the 320 over r squared is equal to 0.12 pi r. And therefore, if I just did the math on that, I'm going to say that r cubed is equal to the 320 divided by 0.12 pi. All right, I think I got the math right on that. So that's the part where I need you to jump in and tell me what that works out to be. What's the r in that case? What is the value of r? R, of course, has to be greater than 0 and all that good stuff. H has to be greater than 0 as well. And, you know, I'm assuming that you're going to get a greater than 0 answer from doing that. Can you help me out, please? What answer are you getting on your calculator when you put that all together? Now, whoa, that's two different answers. I get 4.39, I get 9.47. Those are not the same. So who is right and who is wrong? I don't know. Vanessa, you're sure about your answer? Ashwin, you sure about your answer? Okay, so Vanessa says she's sure, but a lot of people. So, oh, Ashwan, are you sure? Oh, it is 9.4. Okay, all right. That's of course in centimeters. And the other thing we obviously need to do is to go back and figure out what the h is by plugging it into h is 2,000 over pi r squared. All right, and I'm going to leave that part for you to do on your own. Right. Oh, round it to 2 decimal places. Did we get 2 decimal places? 9.4. Okay, right. Okay. All right. So I'm assuming you can finish up that question on your own because the question, let me make sure the question is answered. It's asked, what are the dimensions of the least expensive? Yeah. Okay. So the dimensions, I need a radius and I also need a height, and I'll leave that to you. Reasonable? We can move on, correct? Everybody good with that question now? Yes, no, maybe so? Very good. Okay, great. All right. So let's move this along. Sally is running at a rate of 9 kilometers north. Catherine is walking at a rate of 4 kilometers east. If Catherine is 4 kilometers north of Sally at 1 p.m., at what time to the nearest minute will they be closest to each other? What is the minimum distance between them? Okay. So we did a question like this before, but I have no objection to us doing it again. So we label the two people looking something like that, where Sally is north of Catherine is 4 kilometers north. So let's put this as being K for Catherine and S for Sally, right? And this is at the beginning at 1 p.m. And this is a 4 kilometer distance here. All right. And so Sally is the one who's running at a rate of 9 kilometers north. And Catherine is walking a rate of 4 kilometers east. Actually, it's the other way. So let me put this on top. Let me erase this here. I'm so scared of erasing right now. Anyway. Okay. So Catherine is walking at a rate of 4 kilometers per hour east. So Catherine is the one who's walking this way, and Sally. Let's see what Sally is doing now. Sally's running. She's running north. Okay, so Sally is the one who is doing this, going this way, and going at a rate of 9 kilometers per hour. And Kathy is the one who is walking east at a rate of 4 kilometers an hour. Okay. And so the distance between them will obviously change as time passes, right? Right now, they're 4 kilometers apart. And what we're trying to figure out, and you can look at things like getting the domain and all of that. That's something you should do, hopefully, on your own. But the next thing we have to figure out is what formula can we use for how far Sally is from Kathy and how far Kathy is along her route at any point in time. So remember, Kathy starts from here and she's walking east. Sally starts from here and she's walking north. So we need some way of coming up with a distance that Kathy is from her starting point and where Sally is from Kathy. We need those two distances. One distance is getting shorter and one distance is obviously getting longer. Okay, so let's start off with Kathy. How far will Kathy be from her starting point as she heads east from where she is right now? Give me an equation that represents Kathy's distance. We'll call it distance 1, right? What would you put for Kathy? Remember, Kathy is the one who's going this way, right? At a rate of 4 kilometers per hour. So distance 1 is just simply 4 times t. Okay. All right, so every hour, she goes another 4 kilometers, right? Distance 2 is Sally, whose distance is getting shorter with respect to where the direction that she's going in. She starts off being 4 kilometers away and walks, or runs, I guess, runs at a rate of 9 kilometers per hour north. So that distance up to where Kathy used to be is getting shorter and shorter and shorter. Give me what that distance is as a formula now, please. Steve did a good job with the first one. So 4 minus 90. Thank you. Okay. So these are the two distances that we would have. And remember, this line, let me just show you what lines we're talking. I've used a different color for that. This line, right, will be one side of a right triangle. And this line is going to be one side of a right triangle. This line is getting shorter as we go along. This line is actually getting longer as we go along. And the distance between them is going to be given by the right side, the hypotenuse of a right triangle. Okay? So what we're going to do now is we're going to put these distances together, right? And we're going to create an equation that gives us the distance between them. And that distance is, as I said, the hypotenuse of a right triangle. So the total distance, we call it TD, will be equal to the square root of, this should look familiar to you, the 4 minus t, 9t, sorry, squared, plus the 4t squared. Does that look kind of familiar to you? Persons who asked me for that question. Do you remember seeing something like that? Let me erase this part right here. All right, whatever the square root of that is, should represent the distance between the two people, right? The distances that you gave me first from Adam and Stephen, those distances are just distances from some fixed point, right? But the distance between them would actually be the hypotenuse of a right triangle that keeps changing as you move, as those two people are moving at different rates. So far, so good. Are we good so far? Quick check-in of the room here. Alexander, how about you? And Ariana, how about you? Ariana, are you good with that so far? Okay, All right. So we know how this works. We can go from here. That means the total distance. Sorry. The total, that's what messed me up the last time. The total distance is the square root of, well, we have a little math to do. 16, excuse me. And that would be, what is that now? Minus 72. 49 is 36 minus 72t plus 81t squared plus 16t squared. Okay. And then, of course, what we're going to do is we're going to simplify this a little bit, this total distance here. And we're going to get 81, 97, 97t squared minus 72t plus 16. Okay, square root of that. And of course, we can rewrite this as a base to an exponent of a half. So 97t squared minus 72t plus 16 to the power of a half means the same thing, as you know. And now we can take our TD prime of, well, whatever we want to call it. Let's call it the distance formula, derivative of the distance formula. So that, I'm sure you remember, would be a half. And we've done this so many times before that I'm sure that everybody is comfortable with this now. The square root of 97t squared minus 72t plus 16, the 2 on the outside here. Then the top would be, let me think now, 180, 194, 194t minus 72. All right, again, you all want to double check me on that. I'm doing mostly in my head here. So messing up is quite possible. Okay, that's what you got as well, Adam. Okay, great. And of course, this is what we need to set equal to 0. And as you know, we set the top to 0. That's the part that we're concerned with. So 194t minus 72 is equal to 0. And then you can solve for t from there. Okay, again, I think it's okay for me to leave. And let me make sure I answer the question, that we'd answer the question. At what time? Okay. So it says at what? All right, let's go a little bit further then. Let's go a little further. So that means that t is equal to 72 divided by 194. And what is that? That works. That's about. What is that about approximately? Give me 2 decimal places. Give me a number for that, please. What does that work out to be? You all have the calculators there. 0.37. Okay. All right. So we have to translate that to a time. Does anybody know how we can do that? Because it doesn't say how many hours or anything like that. It says it wants a time. We started at 1 o'clock, right? To the nearest minute. Can we put that into a time? Is that possible to put that into a time? How can we translate that into a time after 1 o'clock? 0.37. What does that exactly mean? All right, started at 1. We're 0.37. How do you get 22 from that, Stephen? 0.37 an hour. And how do you do that? How do you find 0.37 an hour? Put it into minutes. You multiply it by 60, obviously, because there's 60 minutes in an hour. So we take the 0.37 and multiply that by 60. And I'm hearing it's 22 to the nearest minute. So it's at 1:22 p.m. is when they're going to be, because it was 22 minutes after 1 p.m. when they started. And when are they, and what is the minimum distance between them? Can I leave that for you? Can I leave that for you to do? Because that's just plugging that into the distance formula, the 0.37 into the distance formula, right? Into the original distance formula, which is this thing right here. Okay, so thank you, Sarah. Thank you very much, and Adam as well. Can I leave that to you now, folks, and we move on? That's just the final number crunching that I think you can all do on your own. Reasonable? Can we move on, please? Yes? No? We can. Okay, Sarah says yes. That's all I need. I'm moving on. Okay. All right. The position, and thank you both, Sarah and Sarah. Thank you both for giving me the go ahead on that. Okay, position of an object is given by the function. And before I go any further, I think you already know my style. So we've been doing this for a while together for you to understand that if at any point you aren't sure about anything that I am doing, just say so, right? And you don't worry about the rest of the class and what they think. What's more important is that you get what we're doing, that you understand what you're doing. So when the test comes, you know what you're doing. Okay, that's more important to me than what the rest of the class thinks. So just so you know. All right, next question. Position of an object, and this is a position function, and they give you an equation. Units are seconds and meters, all that good stuff. Find the displacement at 3 seconds. Okay, so the displacement means where are you? Right? Where exactly are you? So that part is hopefully easy enough. And that's just simply taking S of 3. All right? And you can do that on your own. All right? Find the velocity at 5 seconds. Well, that's going to be the S prime of S prime, meaning the same function derivative at 5. So again, I don't make any assumptions that are wrong. Is it okay for me to assume that you're okay with doing those two parts of the question? Finding the displacement at 3 seconds, finding the velocity at 5 seconds, and find the acceleration at 2 seconds, right? So the acceleration at 2 seconds is going to be x double prime of 2 seconds. Okay, so Adam says he's okay with that. Is everybody else okay with that as well? Or do I need to do more? Okay, so everybody seems to be okay with that. So let's leave that part out of it. Okay, let's get to the part that I think people might need some help with. When is the object slowing down? When is the object speeding up? That's okay, that takes a bit more work. So here's what we're gonna do. We're gonna find we know that we have to compare our velocity with our acceleration. That's the way this is done. So I'm going to get my S prime of this function first, which is equal to S prime t. Let me do this better. Which is equal to 3t squared minus 19.5, that's 39t, right? And my S double prime of t is equal to 6t minus 39. Okay, so those are our two functions. One represents velocity, so this is the velocity function, and the other represents acceleration. Now, I think the way I'm about to do this is the best way to do it. That's what I think. Okay? So what I'm going to do now is I'm going to do a little diagram of each one of these things, and I'm going to put it on a number line. S of t as a plus 90 at the end. Oh. Thank you. Thank you very much. Yes. Plus 90. That's actually important. That's actually very important. Thank you. That doesn't affect thank you, Adam. That does not affect the acceleration function, but it does affect the velocity function. Okay, so I'm going to go ahead and try to draw this function, but it's a good thing you mentioned that because now I'm going to go ahead and factor out that 3. So it's the same thing as this. S prime of t is the same thing as 3t squared minus 13t plus 30. I think I got that right. Yeah, okay. So this factors into t minus 6 and t. No, that's not right. Hold on, let me just think. 10 and 3, sorry. 10 and 3. Minus 10 and t minus 3. I think I got it right that time. 10, yeah, okay, good. Okay, and then I can draw this. Right? I'm going to draw a little diagram on the side here. Nothing elaborate, just a little sketch of this function because I want to ask well, let's draw a sketch of the function. This function is a quadratic function that has two zeros at 3 and 10. And I think you'd agree with me. It looks something like that. Okay? The second function is the straight line function, the acceleration function, 6t minus 39. So that one is a much easier diagram to draw, hopefully. So actually, I don't even need to write this down. We're just going to draw it. We don't need to factor it or anything. We're just going to draw it. So here comes my second. I'm not going to draw them both on the same thing. I don't want to do that. I'm going to draw it on a separate graph. So here's my little sketch of a straight line function that has a slope of 6 and a y-intercept of minus 39. So it's somewhere down here, minus 39. And where does it cross through the x-axis, by the way? Can somebody tell me what the x-intercept of this is? All right, so I'm talking about this function right here, 6t minus 39. What's the x-intercept of that function? I say x. I meant the t-intercept of the function. What is the t-intercept of the function? So 39 divided by 6, you just take that, set it equal to 0, and divide it through, you're getting 6.5. Okay, so 6.5. So that's going to look something like this. 39 here. Hold on. So that's going to look something like that. Okay, what I'm about to do now is draw a set of number lines on top of each other, right? And we're going to see if we can figure out what the overlap is for where they're both negative or where they're both positive. All right? Okay, so let me start off with the velocity function. I think I can put a number line in from the, yeah, I think there's a math number line in here. Number line, here we go. It's up here. So I'm going to take that number line, bring it down. Okay. So this number line, hopefully it has enough on it for me to work with. This number line, I'm going to be drawing some regions on it for the velocity function. I want to draw where this velocity function is positive. I'm going to need two number lines. Maybe I should clone this first. Okay, so I clone it, but I can't find it. No, don't do that. I can't find the clone. All right, doesn't matter. We'll, all right, we'll just go. So this number line, I'm gonna put where velocity is positive on it, right? So I'm looking for velocity positive. So positive on this number line means that I'm going to be going from, remember, positive means it's above the x-axis, right? So I'm going to be going from here to the right. And I'm going to be going from here to the left. Can we all agree on that first of all? Right? Does that make sense, first of all? Just want to make sure that that makes sense. That number line is consistent with the graph. Positive means to the left of 3, to the right of 10. Now, I should point out that I really shouldn't go more than 0 because, in fact, yeah, let me stop at 0 because it really, there's no time that makes sense if we go less than 0. So let's amend that a little bit. Let's go up to 0. Okay. All right, so let's stop here. Say from 0 to 3 and from 10 onwards is where that one is positive. Now look at this graph down here, the second graph. This graph for the acceleration is positive when you are greater than 6.5. So I'm going to go in here with a different color now, make it green, and say 6.5 is somewhere around here. And I'm going to go to the right for that one from there. Okay? So right away, I know one of the places where this thing, and that's the only place it's positive, by the way. It's only positive once you get past 6.5. So can we agree on that? All right. So if that's the case, when they're both positive is where? Where is it that they're both positive? Can you tell me right now where they're both positive? After 10. Perfect. So when x is greater than 10, or t, I should say, greater than 10, they're both on the same page. Now let's come down here. I really need another number line. And let me see if it's going to cooperate with me a little bit more now. I need you to clone yourself. Clone. There we go. Okay. So here's my second number line. I want to try to do a thing now where they're both negative. Right? I find the number lines work for me. It may not work for you, but they work for me. So I'm going to put now where this function is negative, and that's between 3 and 10. So I'm going to go ahead and say they're both negative between 3 and 10. So I'm going to put a red line there as well from 3. Actually, I meant red. From 3 to 10 is where one of them is negative. And then I'm going to put where the other one is negative, and that's from 0 to 6.5, right? If you look at where I'm pointing from 0 to 6.5, and put that in green. From 0 to 6.5, somewhere around here. All right. So this is negative on the red line for the velocity. This is negative for the green line on the acceleration. Where do you see them both overlapping? From where to where do you see the overlap taking place? From 3 to 6.5. So I'm ready for my answer now. My answer is that they are speeding up. They're speeding up from 3 up to 6.5, union with 10 to infinity. Now, I don't really have to draw the number lines again, because anywhere they're not speeding up, they're slowing down. So I can confidently, so if we accept that this is the answer for speeding up, I'm not ready to write slowing down everywhere else. I mean, apart from being stationary, and they're stationary, when the velocity is 0, by the way. But they're slowing down when, so remember now, it was 3 to 6.5. So that means that anywhere from 0 up to 3, they should be slowing down, right? Between 3 and 6.5, nothing is happening. Well, not nothing is happening. They're speeding up. Union with, and you can draw a separate number line when they're both negative. Sorry, one is positive, one is negative, if you want to go through that. And then I'm going to say from 6.5 now up to 10. So it's everywhere else is basically what I'm saying. So I personally like the number line approach. You don't have to use it, but I think it's a very visual way for you to easily see where overlap is taking place. All right. So, that's my take on it anyway. Does that kind of clear that up for you? Does that help you out with that? Does that make sense to everybody? Yes, no? I want to move on to the last question, but I need to be sure you're following that. Okay, good. So I'm going to move on now to what I think is one more question that we have here. Manufacturer, okay. All right. So this is a cost function. Yeah, you're welcome, by the way, Adam. You say cost function. So if I want to know the cost at any point in time, I just simply put the number of jackets that I'm making into the cost function. Because X is the number of jackets that I'm making. What monthly production level, by the way, that's monthly cost. What monthly production level will minimize the average cost per jacket? Round your answer appropriately. The average cost per jacket. Well, how would I get an average cost? Think about yourself as a business person right now, right? And you want to know how much is the average cost for each jacket that you're making, right? So you know what the total cost is, because this function right here, This equation right here tells you what the cost at any point in time. At any point in time, one of the costs, you plug in X, you plug the number of jackets into that function, it tells you what the cost is. The total cost tells you what the total cost is. But I want to know the average cost, right? What does each jacket at any point in time cost me to make? Right? Is it $20? Is it $50? I'm not talking about the overall cost of making all the jackets. I'm trying to figure out the cost of one jacket. So look at what Taj just says. Put the total cost over the number of jackets. Right there. Right there. Exactly right there. What Taj just wrote is brilliant. Right? Take a bow, Taj. Right? If I want to know what the average cost of each jacket is, take the total cost that I have, just like when you're doing your marks. You take all your marks, put it over the number of marks that you have. It's the same thing here. So what does that equation look like? What is my unit cost, or in this case, average cost per jacket? So cost per CPJ, I guess I could call it that. What's the equation of the CPJ? Well, I know that the cost is the function that's underlined, right? So the 0.02x squared, that's my total cost, plus 300x plus 12, looks like 1,000, right? So what am I going to divide that by? Am I going to put that over? And Sarah says, put it over x. Absolutely. Absolutely. Okay. Now, for me, speaking personally, all right, I'm not going to use a quotient law on this. There's just no way I'm going to go quotient law on this, right? What do you think I'm going to do if I had this question? Because you know you have to find a derivative now, right? You know that's the next step, right? So if I have to find a derivative and I wanted to make it easier for myself, what do you think I'm going to do? Say x to the minus 1, make it a numerator. You're on the right track. All I'm going to do is I'm going to divide x into each one of these things. I'm going to divide 0.02 x squared by x plus 300 x over x plus 12,000, that is, over x. That's what I'm going to do. Because if I have a common denominator of x, it means that x is dividing into each one of those things. Now, look at how easy this is. This is just going to be 0.02x. This is going to be plus 300. And this is going to be plus 12,000, sorry, times x to the minus 1. That's all. Right? So just divide each one of these things by x. It's the same function that we had before, except it's just dividing each of the separate terms by x. So what that means for derivative purposes is this. This is going to be 0.02, and this is going to be minus 12,000 over x squared. That took me all of 10 seconds to do. And I think you can see how much easier that is than me even considering doing this as a, hold on, let me just make sure I wrote the question down right. It's the x squared, right. Even considering doing this as a product law, sorry, a quotient law, or anything else for that matter, right? So sometimes you can make your life a lot easier, and I'm all about that, by the way. Let me just tell you that right now, and I have no shame about that. I'm all about making it easier for myself. I'm going to find the route that is the shortest, easiest way to get to where I'm going. All right. So anyway, so obviously you're going to set this equal to 0, right? So that means that you're going to end up with 0.02 being equal to the 12,000 divided by the x squared. I don't know, I have an extra thing over here. All right, anyway. So that means that if I cross multiply, x squared is equal to the 12,000 divided by the 0.02. All right? And I'm going to leave that with you. Now, you're going to get 2 answers because you have to find a square root, obviously, at some point. But I would advise you to only consider the positive value because X is number of jackets. The other thing that this question involves is it says round your answer appropriately. Please remember that the X that we're talking about here represents jackets. So we should have a whole number. So you should either rounding it up or rounding it back, whichever one makes more sense in this case.